My name is Emily Woods, and background mechanical engineering and renewable energies from Georgia Tech. I had the privilege about 2 years ago to actually be part of my own startup called Sanitation. We've been doing some different ideology, basically ideas that we had both from Georgia Tech Research Institute and Emory's School of Public Health about ideas of sanitizing human waste. And we were given a grant from Startup Chile to separate from the university, move down there, and actually try out some of our ideas. It was an incredible opportunity. I think what scoped a lot of how I think now was when I first got down to Chile, I had the opportunity of living with a family in a peri-urban slum outside Santiago for about a month. And even though I really didn't speak any Spanish and they definitely didn't speak any English, I learned a lot from living with them, from seeing their life, from seeing how hard they worked. I'll never forget, so we were building a roof with the dad of his family, and there was, minimal resources that we had and no money, and he asked my ideas. He's like, well, what are our options for fixing the roof? And I was like, well, one option, it's more simple, and he stopped me right there. And he said, Emily, if an option is more simple and it's a possibility, go with that. And so I think that scoped a lot of what I've been doing in my work now and where we went with solar sanitation. So a lot of this conference has been about alternative treatments, and I think the reason why we should care is because the current sanitation methods for treatment are not working, both in health standpoints and feasibility standpoint. The director of global program from the Gates Foundation said it best. He said, the bottom line is that while on-site sanitation has potential to serve the needs of billions of people, we are facing the environmental impacts of complete market failure when it comes to creating safe and affordable ways to process accumulated fecal sludge. So from a health aspect, who did some studies saying that a lot of conventional wastewater treatment systems are really missing out on helminth removal. And then we even found from Corrales and a few studies done in Central America that actually in places that use UDDT, where people were told that their waste should be clean enough to put on their crops, they actually had a higher prevalence of diseases. Because what they're finding is that helminth egg and a lot of the other very resistant pathogens weren't being killed off in normal methods. From a feasibility standpoint, this is actually another study that was republished, looking at some of the main ways out here. Now I realize that at this conference that we're at, there's a lot of interesting ideas out there, but this is more the ones that we've been working with for a while. So looking at both conventional sewage, septic tanks, waste stabilization ponds, and then we kind of compared it to what we found simple solar waste treatment and how it compared to them. You'll notice it's a lot cheaper, very high helminth inactivation, very low operator expertise required, and actually zero permanent land. Everything that we did was based on a mobile. We're dealing with a lot of these peri-urban slums in Santiago where people are in and out constantly. So you have to have a treatment system that can change with constant changes of people. And I'll get to how we got to some of these in a second. The reason why I'm interested in solar is because when you look at the world, when you look there on the left, that is the highest prevalence of deaths due to diarrhea. So where we can estimate that the worst sanitation coverage is, it almost exactly relates to some of the highest solar radiation in the world. So that just kind of gives me excitement. Here on the left, this is a project that we started working on a long time ago. These are the initial solar latrines in Bolivia, built with Emory, Georgia Tech Research Institute, and an NGO there called SuSanA. While this was fantastic, it reached some higher temperatures. Basically what they were looking at is to increase the decomposing, that's the word I'm going for, that was going on in the volt latrines. It wasn't going fast enough, it wasn't going thorough enough. So their idea was that if they could heat it up, maybe we could speed it on and make it a little more thorough. We took that idea and took it to the next step. So what you see on the right is what we were working with down in Chile, and that's what we tested. And a lot of different ideas went to wire design. I just want you to get the basic idea. A very simple solar parabolic concentrator, which uses the sun's energy to heat up right there in the middle, is a steel drum that is filled with just the solid fecal waste. What Mr. Summers was just talking about is a lot easier to heat up just the solid waste as opposed to the mixed stream, so we focused on the solid. So some of our research goals were down in Chile was to demonstrate that solar concentration is more effective at pathogen inactivation than common pit latrines. Pit latrines are the main thing that people use down in Chile. We wanted to determine the exact time needed to kill off even the most resilient of pathogens, and then we wanted to evaluate the actual practical feasibility. A lot of people have been talking, it's not just the technology, it's the whole entire system. So we were trying to look at it from a systems approach, and we really wanted to come up and see if solar treatment could fit in various different solar sanitation solutions, the entire method, and how we could kind of use that down in Chile. So first off, a lot of people have been asking about how we actually did our helminth inactivation. So first off, you need to acquire an indicator organism. Most people use ascaris because it is high prevalence, it's high resistance. Sadly, Chile does not have a high prevalence of ascaris, but thanks to some tests done by Meyer, she actually showed that, they showed that there is multiple different in the helminth family that have the same temperature resistance. So Toxicara canis, which is actually often found in puppy poop, does have a high prevalence. So if I wasn't standing out enough in Chile being a female, blonde, white girl, imagine me chasing down this family of puppies for a week in downtown Santiago collecting their poop. People got a kick out of that. But that's what we use for our indicator organisms. So once collecting this puppy poop for a couple weeks, we used the method, the ammonium bicarbonate method, that was used actually here in Moody in South Africa. They came up with that. And it's a way of isolating the eggs into a very, very strong stock solution. And then we used the tea bag method, and that was done by Jensen. And the idea is to use small nylon discs that have 30 micrometer sized pore holes. Most of ascaris eggs are going to be from 40 to 70 eggs, 70 micrometers long, so it won't be able to slip out of the bag. And so as you see, kind of the method here is that from our stock solution, we're injecting these homemade tea bags up with 1,500 eggs in each bag. Then we got to use that to actually spike our different poop samples. So this is our methodology first for the comparison. So we created our tea bags filled with about 1,500 Toxicara canis eggs. We then placed our tea bags in 3 different conditions, from our controls to our homemade solar concentrator, which you see there, which we made down in Chile, and then also our homemade pit latrine. I'll talk about that in a second. And then we removed these daily at 10 a.m. for a week, incubated for 3 weeks, and then there on the far right, with help from the veterinarian clinic down in Santiago de Chile, we analyzed each of our different eggs that we found there, counted out at least 100 eggs in every single sample we were taking, and it's very obvious which ones were inactivated and which ones were activated. So this is kind of our results that we got as far as temperature. So, like I said, the solar concentrator here, you'll see kind of our dimensions where our tea bags are placed with the temperature probes. And the zone of safety, that's a theoretical, basically, zone of safety done by FSM, where ascaris will be killed off and at what temperatures. So we wanted to make sure that we were hitting above 60 degrees Celsius, and what we found that entirely throughout our still drum there is that we were hitting over 60 degrees Celsius for multiple hours a day, so it's a good sign for us. And our pit latrine was interesting because, like I said, we're at a veterinarian clinic. They're not too keen on us jigging giant holes and having a lot of people poop in them. So we had to do our own kind of makeshift one. It was very small, 20 centimeters by 30 centimeters. We actually just used animal feces that was found there in the veterinarian clinic. And you can tell these from these temperatures that even though ambient was only hitting 30, in the pit latrine we're hitting 40, 45 degrees, which is very unlikely in the pit latrine. But it maybe count as the most extreme case scenario. So if we could beat that, then we're doing quite well. So here actually is our viability results. In our controls, we had anywhere from 85 to 95% viability. And then the red line that you see there, that's actually the pit latrines. The brackets are the range. The points are actually the average. And then our solar concentrator. So first the pit latrine, like I said, it was a very extreme case, pit latrine there. But we still saw a long time die-off. If you notice though, our solar concentrator in each of our tests, that in 24 hours we're having over 3 log inactivation. That was really incredible for us to see. And if you'll notice that there's not even a range on that. It was straight across the board. We're hitting 99.9% inactivation of helminth, or of Toxicara canis. That's what we're using. So that was very obvious for us that we have got, even the most extreme pit latrine, we're still doing better than them. So next was to actually determine the length of time that it took to achieve the WHO pathogen requirements, which is 3 log inactivation. So we had the same setup, went around, chased some more puppies, got their poop, made these tea bags, and this time we put it back into our solar concentrator, but did it on an hourly basis. And so that's what you kind of see here. And it's pretty cool to see that at 2 hours, still nothing had taken in, but by 4 hours we were hitting 3.5 log inactivation. So that was incredible for us to see that in only 4 hours, 99.9% of even the most resilient pathogens were killed off. So moving on, then we looked at the feasibility and exactly how to make this into a full system or combine it to other systems. So since we'd already proved it down in Chile, we used some engineering to relate what that would be like in Kenya. Our next project's going to be here in Kenya. So we looked at the solar radiation that they receive here in Kenya. We looked at what the minimum is in a month, or the max and the averages, and knew that our efficiency of our system was about 45% down in Chile. And so looking at that in a worst case scenario, so for the worst month in Kenya, it needed to be about 2.6 square meters parabolic mirror, on average 1.7. The basic cost to make that here in Kenya is about $300. The drum that you see there that it's sitting, we can design the drum and the system to be anywhere from 40 liters to 80 liters big, which easily will handle about 100 people. The smaller one, the 40 liters, will handle 100 people's waste, solid waste, in an alternating method. So our idea was, instead of to touch the waste, that we actually have people pooping straight into the steel drum. And so that steel drum is collected on either every other week or once a month, whatever works, and then that is directly put on the solar concentrator. So it allows the solar concentrator to be used every day by different families, that multiple families can own these. So if you're looking at the breakdown, it came to less than $1 per person. So that was exciting. What we did to do our feasibility was using a slice method that actually got to help develop GTRI. The idea is to combine literature review, stakeholders, looking at a fully multidisciplinary team, and then field testing to actually get your CTQs, your critical quality points. And that's how we moved from the individual solar latrine that you saw there in Bolivia to the more communal one, the mobile one that you saw there at the end. And so we talked to a lot of different people from around the world, talked to a lot of people here who are here now at this conference. That's kind of fun when you get to put a face with someone's name who you've been talking to for a year. And this is the system that came up. The idea, like I said, is to rent an in-home toilet to the families. This is what we did in Dunniwe in Chile. So they rent in-home, collects the waste there in these steel drums. People come by, they pick up the steel drums. They are then transported to these decentralized mobile solar parabolic mirrors. There it's decontaminated in less than a day, and the idea is then to use it for fertilizer. Some of the things that we found a lot while we were down there is obviously the basics of any treatment system you're looking at is low infrastructure, low investment costs, easy manufacture. We wanted something that we could make there in the slums, there outside of Santiago. Robust, durable, not prone to theft. This thing would be hard to take, and people weren't very interested in it. This is also interesting that we found worked a lot better in Chile when you had a service. The service allowed us, sanitation service, is quick customer feedback, the user acceptance, and quickly indicate where the system's going. And then this was also really interesting for us, is the revenue streams and where that was coming from. A lot of people are focusing on making money on the back end, which is awesome, but what people cared more about was getting the shit out of their home. And so if we could fund our entire system by just using that revenue stream of just the idea of waste collection, then any money that we make or don't make on the back end would just be bonus. And so that's what we kind of designed it for. Some of our limitations that we found down there is, like I said, our pit latrine was a little interesting while we were hitting over 10 degrees Celsius above the ambient. Normal pit latrines are only going to be about 1. We saw a lot faster inactivation in our pit latrine than was expected. Most people after 6 months or even a year, helminth is just beginning to be inactivated in pit latrines. And then we saw high variance. I think all this is because of the pit latrine, its size, its dehydration, the fact that our cover material was a piece of sheet metal on top of it. And so that increased the temperatures, but it kind of gives us an extreme case compared to. And the other part is that we assume that Toxicity had exact resistance to aspartate. And while we know that the temperature resistance is the same, there's a lot of other factors at case. So this coming year, we'll be working in Kenya, and we hope to do it with actual aspartate, the same test kind of comparisons again. So our conclusions is that solar concentration is more effective at meeting WHO requirements of 3 log reduction than the minute latrine. That in basic, simple solar concentration at 4 hours in Santiago, Chile, we saw complete inactivation. And then we also saw that solar concentration shows promise to be an effective and feasible waste treatment. What we saw also as we talked to other people about their current waste solutions that they have for collecting and storing, that solar is a great way that can be, it's flexible, so it can be inputted in a lot of different other designs and a lot of other systems. Like a lot what Scott Sumter said yesterday, where it's not about the technology, it's about the whole solution and fitting the technology to that. And I know that this is so flexible and so easy to use, it's something that can be used now in a lot of different places. Some of our key learnings and takeaways is the methodology combination to actually do our aspartate testing. That went very well. We learned a lot from doing that. The fact that if you're going to try and test a pit latrine, get a real one. And then we're going to validate our pathogen trials side by side here in Kenya this next year with GIC. So big thank you to everyone that helped us out. from Startup Chile, from our grant, to the veterinarian lab that we had down there, to Emory and Georgia Tech. I couldn't do it without you, so thank you. Questions?